Hey guys, hi once again. Today is day 46 of my algorithm video, and I just want to record this before going to the gym. Um, with the algorithms, it's quite complex. I know my end goal, which is acing the coding test, and getting into one of the FANG as a software engineer, or maybe AI, which I majored in, although I would have to do masters in order to get employed. But um, it's a long process. It's a long process, and um, I know that I'm heading towards that goal step by step. So I'm being really patient and just paving my day every day. And I'm very thankful that you guys are joining me in that journey. Anyways, enough said. I'm gonna move on to reviewing the monotonic stack and reversing reversing a linked list and some other templates today. So bear with me. I'm going to share my screen. Yes. So yesterday we ended at fast and slow pointer, although we didn't have any example. I've included some example for the finding number of subarrays um, and monotonic increasing stack. So yeah, I'll show you in a bit. But as for the reversing a linked list, you can see that this was a template that we went through. Remember, current is a pointer to the current node being processed. So we start with the head of the list. And then here, the previous is initialized to none and will be used to keep track of the previous node as we iterate through the list. And uh, for the linked list, we usually have a while loop. So while the current exists, so if it's not none, then at the end of the list, current will be none and the loop will stop. And here is the most important part. Next node is current next. So it temporarily stores, the next node temporarily stores um, the node in the list so that we don't lose track when we change link. And then um, we, the next pointer is reversed now because yeah, it's previous. Toch? I mean, right? Um, so instead of pointing to the next node in the linked list, um, it now points to the previous node, which is previous. So now we move the previous pointer to the current node. And this is done so that in the next iteration, the next node can point back to this one. And we finally move the current pointer forward to the next node in the original list. We store it in the next node. And then at the end of the loop, the previous pointer will be pointing to the new head of the reverse list. And this function returns this node as a new head of the new linked list, which is the reverse list. So um, yeah, this can be used in many different scenarios that we have looked in. And usually for the linked list, they explicitly tell us that we have to use a linked list. So it's either fast slow pointer or this reverse linked list. The main ones are. For this one, it is designed to find the number of subarrays that meet the specific criterion. So um, it takes two arguments, the list of integers and the k, the target sum we are interested in finding among subarrays. And um, as you can see here, counts is the dict, so the hash map or dictionary in Python of integers used to keep track of the number of times a particular cumulative sum has been seen, and counts. This initializes the count for the cumulative sum 0 to 1, and this is crucial for handling cases where a subarray itself equals to k. And current, as you can see here, it will be used to store the current cumulative sum as we iterate through the array. So yeah, we do the iteration through the array, and we update the cumulative sum. Um, um, so we do some logic to change the current. So it keeps on updating the cumulative sum current based on the number. And although it's missing here, it would usually look like this: current plus num, something like this, or minus whatever the question asks us to do. And after updating current, it will hold the cumulative sum of elements from start of the array up to the current element, which is num. And then after that, we count the valid subarrays. So it checks, this line checks how many cumulative sum the current minus k has seen before. And if the current minus k is seen before, then it means that there is a subarray ending at the current index whose sum equals k, right? So this is because, like we did here, um, yeah, I just wanted to show you guys that code was a snippet of the extension of the array manipulation. So something like this, you know, right minus left plus, no. Okay, I'll just write it here. Uh, so if current minus k has been seen before, it means that there's a subarray ending at the current index whose sum equals k, because current minus the current minus k equals to k, right? So uh, we update the counts dictionary by 1, and then after that, after checking for subarrays that equal to sum to k, the current cumulative sum current is added to the counts dictionary, increasing by count by 1, and return the answer. Yeah, we were doing the linked list, but now we were doing this question briefly because it was part of the curriculum of the NEET code that I was looking at. So I just wanted to include it. Okay, so this part, monotonic increasing stack. So it was a rather unique chapter, this one as well, monotonic. So what was a monotonic increasing stack? It was a stack data structure. Remember the stack, right? Um, that maintains its elements in an increasing order. So if you push elements onto the stack's element will always be the smallest element, and the elements will increase as you go deeper into the stack. So you see here, we initialize the stack array as an empty list, and then also the answer as 0. And we do a for loop in for array, and for monotonic decreasing, we just flipped this equal bigger sign into the opposite end. Um, so while stack and the end of the stack is more than num, so while loop checks if the stack is not empty, so while stack, and if the top element, so the end element, is greater than the current element, which is num, right? And then we do this logic, some kind of logic here, which I'm going to show it in the example soon. And then we did stack.pop, which was just removing, just like how we remove from the queue as well. And then if the while loop ends, we append the current number after ensuring that the stack maintains its monotonic increasing order. Then the current element num is added to the stack. And finally, the function returns answer, which may have been updated during the processing of the array. So that's answer. Yes. So this is the example of the question that uses monotonic increasing stack, and that's trying to find the next smaller elements in the array. So the stack keeps an element, indices of elements in the array, and as you iterate, the current element is smaller than the element corresponding to the top index of the stack. So the current element is the next smaller element for the element at that index, right? And the result will be the final array would indicate that the next smaller element for each element in the input array. And if there is no smaller element, it will return, well, -1. So, yeah, you can see here that we initialize the result array with -1. So just going through the index, and like we saw in the template, while stack exists and top of the stack is bigger than the current number, which the index is pointing at, then we remove the index and we replace the number with the next smaller element for array index. And then if not, if we found all the next smaller element, then we append the index to the stack, and then we return the result. So if we, for example, use this in this code, it will return the output 1 -1 3 -1. So yeah, that was it, guys. We still have some reviews to go on, but I feel like this is a good way of refreshing our memory. So yeah, if you guys have any questions or suggestions, let me know in the comments down below. And yeah, see you guys in the next video. Bye.